It is taking time. Shall we start? Or okay. Recording. Yes. So in the last class, we have considered this problem. Calculate the design compressive load for a stanchion ISHV 350 at 710.2 Newton per meter, which is having 3.5 meter length, and the column is restrained in direction and position at both the ends. That means to say it is fixed condition at both the ends. We should use steel of grade Fe410. So what we have made initially, based on the fixed condition, the column ends are fixed. So for that, effective length value we have considered 0.65L, which is given in table 11 of page 45 IS 800. So the effective length of column we got is 2.275 meter. And after that, based on ISHB 350, looking into the steel table, we have noted down some sectional properties. That is, what is the height of the section and what is the effective area, breadth of the flange, thickness of the flange, thickness of the web, and IZZ, IYY, RZZ, that is radius of gyration values in both ZZ and YY plane. So after that, to determine the buckling class, which is given in the table 10 of page 44, height to breadth ratio. If you open this table 10, you'll understand height is given as 350 and breadth of the flange is 250, which we got 1.4, which is greater than 1.2. So the buckling class will be A because it is fails in ZZ axis. We should consider. Same way, if it is in YY axis, buckling class will be B. So after that, we should calculate what is the effective area. So to calculate effective area from the table 2, epsilon value is square root of 250 by Fy is 250, so we got 1, and the effective depth, that is after deducting the thickness of the flange and root radius, we got this value, that is 306.6, and breadth to thickness of the flange ratio is 10.78, which is less than 15.7 epsilon. Same way, depth or web height to thickness of the web is 30.36, which is less than 42. So we considered the section is semi-compact. All this we have studied in the last class. So effective area we have taken is 9221 mm square, which is available in the steel table itself. And next, to calculate FCD value or design compressive strength, we have two methods. Method 1 is going through these steps, which is given in page number 34, that is 7.1.2.1 class. Just follow the steps. This is method 1, which is very lengthy. All these comes in method 1. I'm just scrolling down. Right now, let us skip to the, or let us do this problem in method 2, which is easier than method 1 and will be having very less time consumption. So this is method 1 ends here. Method 2 is using table values, which is available in IS 800. So we have noticed buckling class A as well as buckling class B, right? So using table values, that is method 2, for buckling class A, about ZZ axis, KL, that is effective length is 2.275 meter, RZZ, radius of gyration in Z plane, it is 146.5 millimeter. If you open the table 3 from page 20, open IS 800, page 20. All of you, if you do not open, you will not understand this. Open page 20 from IS 800. Opened. In that KL by R, if you do, we will get the value of 15.53, which is less than 180, because what is the starting value of KL by R? Open buckling class A. In the IS 800 page, IS 800 codebook, design compressive stress FCD value.
Ravi Kiran, not able to hear, not hearing anything.
Ravi sir,
Puneet, I think he disconnected. Maybe he will join
yes
again.
sir, I think he disconnected, I guess. I will text him on WhatsApp, sir. Let's see.
Okay, can anyone tell where exactly I have left the meeting?
You were asking us to refer to page 20, sir.
Page 20. Okay, buckling class A is completely done. Buckling class A procedure. Hello, Puneet sir, Chandrasekhar sir.
Yes, Ravikiran. I think
So
Puneet.
buckling class A is completed and buckling class B you're supposed to explain, right?
Yeah.
Okay. So for buckling class B, we need to do same procedure in terms of YY axis. For that, we should consider radius of gyration in YY axis, that is 52.2 millimeter, and KL value, that is effective length, remains same, that is 2.275. If you do KL by R, you will get 43.58.
Ravikiran, you
yes,
are
sir.
not sharing. You are not sharing the page.
Not sharing. Now?
Visible, sir.
Okay. Yes, it is recording. Yes, for buckling class B, we should do the same procedure as we did for buckling class A. That is KL by R. KL remains same, that is effective length, and R values in terms of YY plane, 52.2 millimeter. If you do this, we'll get 43.58. Again, we should open IS 800 of table 3. In that left side, we have KL by R values. In the right side, we have yield strength.
Ravikiran, you started
Yes, sir.
recording? Okay.
Yes,
okay.
sir. Yes, it is in
Okay,
recording mode.
Okay, thank you.
Okay. So right side for 250 yield strength column, if you look at for 40 KL by R value, you will find FCD value as 206, and for 50 you will find 194. But we want for 43.58. For that you need to do interpolation. So if you do interpolation, FCD value will be getting 201.7 Newton per mm square. So once we got FCD value, what is the design compressive strength? PD is equal to area into FCD. Effective area remains same, what we have noted down from the steel table, that is 9221 multiplied by FCD is 201.7 multiplied by 1 divided by 1000 will give us 1860 kilonewton for buckling class B. So what you need to observe here is design compressive strength is lesser for B, correct? For A, what is the value you receive? It's 2088 kilonewton in ZZ axis. For Y, you received 1860 kilonewton, correct? So actual strength is, or what we should supposed to consider is PD as 1860 kilonewton, because in this plane it fails first. Okay, so for design purpose we should consider 1860 kilonewton. Sir has mentioned some notes. It is very important. First method, generally when we have, if you really want to understand or if you have much time, then only you can go with the method 1. And if not, go with the method 2 to calculate the design compressive strength, as it is short and quick and easier. If RYY is less than RZZ, the column will buckle about YY axis. So if the buckling class is the same. Therefore, the design compressive strength is governed by effective slenderness ratio, that is KL by R. Here R what you are using, that is RZZ or RYY, matters a lot. In such a case, it is enough if we calculate the design compressive strength FCD based on KL by R in terms of XX or Y or ZZ or YY. For an average column height of 3 to 5 meter, the slenderness ratio, that is KL by R, falls between 40 and 60. So this is very important because sometimes it will not be given, or we have to be in a position to assume these values. Okay, sometimes sections will not be provided in the question. At that moment, we should be in a position to assume these values based on the problem or height of the column. So during preliminary design, this is the value we should assume. If the value in this range is assumed, the result will be a very satisfactory design stress estimate. If the column is appreciably longer, a value little higher than 60 may be assumed. That is more than 3 meter or between 3 to 5 higher the column length, you can choose higher the value. Okay, this note is very important. After the class also just go through once. Let us move on to the next problem. That is, design a column to support a factored load of 1050 kilonewton. It is given factored load. The column has an effective length of 7 meter. Effective length, it is mentioned 7 meter with respect to Z axis, and 5 meter with respect to Y axis. This is also important information. Just observe. Use steel of grade Fe 410. Design load Pu is directly given as 1050 kilonewton, and this is what the section. See, vertical member, what arrow is moving can be considered as column, which is having 7 meter height, and the other section. So one more section is there here. See, that is from the bottom, it is 5 meter KLY direction. This is in Z direction 7 meter, and in Y plane or Y direction it is 5 meter height is given. The effective length about ZZ axis KL, K is constant, L is effective length, but it is mentioned directly effective length. So KL becomes as it is. Same way effective length for YY axis, effective length is 5 meter. So we shall select in section. Just observe, in this question section is not given, right? ISHB. In the previous 3 problems the section was mentioned, but here it is not given. So in this case we should assume the slenderness ratio based on the height of the column. That is why this note is important. Okay. So now based on the height of the column, see buckling class given in table 10 of page 44. As we don't know the section yet, let us assume buckling about ZZ axis, that is buckling class A, and buckling about YY axis, that is buckling class B, because both the section or planes are given, ZZ and YY. Because we do not know the type of section yet, we shall assume a slenderness ratio of 80 to 100. See, we are assuming here. Shall assume KL by R value as 80, so that IYY is less than IZZ. Obviously, then the radius of gyration will be RYY will be less than RZZ. We shall use the buckling class of B. Then what happens? FCD value for this 80 value. If you open table from the IS 800, that is 9B of page 41, KL by R value we have assumed 80. For that directly you can get the value of FCD, that is 150 Newton per mm square, corresponding to yield strength of 250. So with this, what we got, minimum effective cross section required is, we know that P is equal to, or ultimate load is equal to, area into FCD. So here we just taken out the area because we should select a section. That section will be based on area. So to get the area is equal to PU by FCD. PU is what? The given load, ultimate load is given, and FCD we just got from an assumption, that is 150. So effective area what we received is, hello, ಕೇಳಿಸ್ತಾ ಇಲ್ಲ ಸರ್, ನಿಮ್ಗೆ ಯಾರಿಗೂ ಕೇಳಿಸ್ತಾ ಇಲ್ವಾ?
ಇಲ್ಲ, ಕೇಳಿಸ್ತಾ ಇದೆ ಸರ್, ಯು ಕ್ಯಾನ್.
ಓಕೆ, ಕೇಳಿಸ್ತಾ ಇದೆಯಂತೆ ನೋಡಪ್ಪ, ನಿಮ್ದು ಏನಾದರೂ ಮೈಕ್ ಪ್ರಾಬ್ಲಮ್ ಇದೆಯಂತ. Okay. So based on area, let us select a section from steel table, that is ISHB 350. This section what we are selecting, that should not be lesser than this area. If you go through open steel table, in that ISHB 350 at 661.1 Newton per meter, the area of that is 8591 mm square, which is greater than the 7000 mm square. First, you should go with the area column. In that area column, you should select beyond this 7000 value corresponding to ISHB values. Initially, we will not be knowing what is this value and which value we should select, which is greater than this area corresponding to that section we should select. And once we got the section, we should write down the sectional properties. What are the properties we generally note down? What is the effective area? What is the height, breadth of the flange, thickness of the flange, thickness of the web, and root radius and radius of gyration, both ZZ and YY plane. And once we got this sectional properties, we should note down what is the effective length. How to calculate effective in terms of length means in I section, we should calculate what is the effective area. For that, D is equal to total depth, that is 350, minus 2 times the thickness of flange plus root radius. This is explained in the first and second problem with the figure. You should imagine that figure. This is the effective length of I section or web portion. So now, keeping this, let us calculate the effective area. From table 2, page 18, we should select what type of section it is, whether it is a compact section or semi-compact section, or okay, I'm not getting that another one. So now, breadth to thickness of the flange. What you should consider for the breadth, that is half of the breadth of the flange. So thickness of flange is 11.6, will give us 10.78 value, which is less than 15.7 epsilon. Epsilon will be square root of 250 divided by Fy. So Fy will be 250, so that will become 1. So this value is 10.78, which is less than 15.7. Same way, and this thing you will understand only if you open table 2, page 18 of IS 800. Same way, depth to thickness of the web ratio, you will get 36.96, which is less than 42. So the section is semi-compact. The whole area of the web is effective because it is coming in that particular zone. Semi-compact. So effective area, what we considered for the section is 8591, which is from steel table. So now, to calculate the design compressive strength, we know that KL by R is equal to, we'll get one value. Corresponding to that value, we should go and find the FCD value. Correct. So now KL by R, effective length is given, and radius we just noted down from the sectional properties, radius of gyration in ZZ plane and YY plane. So these are the values we got. Next, out of the above values, see, two values we have received, right? Out of the above value, or two slenderness ratio values, KLY or RYY is 93.63, gives lower value of design compressive strength. Right? See, 93 and 46. So with this, from the table 10 of page 44, if you go through, again, height to breadth of the flange is ratio, thickness of the flange is 11.6. If you open table 10, you will understand this one. This fails due to or ZZ axis, that comes under buckling class A. Same way about YY axis, that comes under buckling class B. So now open buckling class A related table, that is table 9B from page 41 in IS 800. So if you open KL by R value for 90, what is this 90 value? Which is available in the code book. but we want FCD value for 93.63. How did you get this 93.63? If you go back, see KL by R value 93.63. For this value, we are going to find FCD value. For 90, it is 134, and for 100, it is 118. What is 93.63? We need to interpolate, and once we interpolate, we get FCD as 128.19 Newton per mm square. And once we got FCD, we can find out design strength, that is PD is equal to area into FCD. So area we noted down from the steel table. So what is the design compressive strength we got? 1101.28 kilonewton. And what is the load given in the question? It has to carry 1050 as ultimate load, right? But for the section what we have selected, that is having or carrying 1101 kilonewton. He has, I mean, in the question it is given 1050 has to be carried, but we are okay with this because this is greater than 1050. So make a line, provide ISHB 350 at 661.1 Newton per meter as column section. If this load what you have calculated, or after calculation, if you get this load as less than 1050, again you should increase the sectional area, and then you can give final section, or which type of ISHB 350, 400, whichever comes safer or carries greater than 1050 load, that should be provided. I hope you understood. If not, please ask me at what point you are not getting it. If you are understood, I'll move on to the next problem. Okay, I'll move further. For a column section, that is next problem, for a column section built up as shape shown in the figure, this figure is provided. Determine the axial load capacity in compression for the data indicated against the figure. So with this figure, some information is provided. What is that information? Fy is 250 Newton per mm square, and length of the member is 6 meter, thickness of the web is 20 millimeter, and thickness of the flange is 30 millimeter. End conditions, both ends restrained in direction and position. That means to say it is fixed condition. Partial safety factor for loads, that is gamma, is given as 1.5. So with this information, we need to calculate for a column section what is the axial load carrying capacity. Okay, so let us follow. So this is the section provided, I section. Here it is welded. The sectional details, what we need to understand. First, sectional details, and next to determine the buckling class, and next to determine the effective area, and next determine the design compressive strength, that is FCD, and next determine the design load and working load. Here it is not design load we should calculate. He has mentioned clearly axial load carrying capacity. So working load we should calculate. So first step is sectional details. What is area of cross? Firstly, we need to calculate the total area. So section is given as, see here, 300 by 30, and this is 500, thickness is 20. Same way, this is also 300, thickness is 30. So total area 20 into 500 plus 2 times flange thickness, flange width into thickness will give us 28,000 mm square. What is the total height? 500 is inner to inner or web height, and plus 30 is flange thickness, that is 560. Thickness of the flange 30 millimeter, thickness of the web 20 millimeter. And what is the effective thickness? That is web, because here, see here, it is not curved. we should consider 500 itself. 560 minus 2 into 30, that is flange thickness, if you deduct, will get effective length as 500 millimeter. So how to calculate IZZ? Is nothing but BD cube by 12. What is breadth for I section flange? It is 300. And what is depth? IZZ. 300 is the web. And what we did here is we considered total rectangle. In the total rectangle, we have deducted this portion. Okay. So total width is 300 into total depth is 560. So BD cube by 12 minus this portion, the hollow portion. 300 minus 20 is the breadth. 300 minus 20 is thickness of web. Total width is 300. In this, if we deduct this thickness from here to here and from here to here, we got, and depth is 500 cube divided by 12. If we do so, we got IZZ value. Same way, IYY value in the other plane. 500 will become breadth and 20 will become depth, because in the YY direction. And next, plus 2 times 30 into 30 will be the breadth and 300 will be the depth. BD cube by 12 will give us in the Y direction. This is the IYY value. Next, how to calculate radius of gyration? That is square root of I by A. If you want in terms of ZZ direction, you should use IZZ value. In terms of YY plane, you need IYY value you should use here. So why we are doing this? We need to check in which plane we are getting lesser value, or in which plane it tries to fail first. Okay, so in YY direction we got 69.51 millimeter, and in ZZ plane we got 229.42 millimeter. So obviously, if we compare these two, RYY is less than RZZ. So RYY value should be considered to calculate the slenderness ratio. So how to calculate slenderness ratio? Slenderness ratio lambda is equal to KL by R. What is KL? Effective length of the column. K depends on support conditions and length L is the actual length. So because the both ends are fixed condition in this problem, we should consider 0.65 L, which is given in the table 11 of page 45 IS 800. So RYY value we just got 69.51. If we do so, lambda value will be 56.10. Now open IS 800, or before that, just we need to check what is the buckling class. For that, bending about YY axis controls as RYY is less than RZZ. Thickness of flange is 30 millimeter, which is less than 40. This will be available in table 10 of page 44 IS 800. We got buckling class as C because in the YY axis. So once we got this buckling class C, you should open IS 800 page 42 to get the KL by R value, correspondingly FCD value. So before that, we need to check what is the effective area. So to check effective area, flange thickness to flange length, same way depth thickness to depth length or web, we should consider. In this, the first one we got, this is we are doing just to check what type of section it is, whether it is a compact or semi-compact section. See, the entire web area is effective and the entire cross section is effective because it belongs to the given value. So effective cross sectional area remains 28,000 and millimeter square. And next, we need to calculate the design compressive strength FCD, that is from table 9C for buckling class C, page 42. Lambda value, that is KL by R value for 50, it is given 183. We got 56.1 as KL by R value in the previous step. Just observe here. K lambda value 56.1. For this, should open code book IS 800 class page number 42 table 9C. In that, for 50 it is 183 and for 60 it is 168, but we want for 56.1 FCD value. Once you do interpolation, you will get 173.85 Newton per mm square. So after this, to calculate design load PU and service load P, PD is equal to area into FCD. This you are aware of this. So effective area is 28,000 and FCD we just got the value 173.85 multiplied by 1 divided by 1000 will give us 4867.8 kilonewton. This is the design load. But what we need to calculate? Service load. For this service load, factor of safety is given in the question. So for this, if you apply factor of safety, that is 1.5, we'll be getting service load as 3245.2 kilonewton. That is 3245 kilonewton. So what is asked in the question is calculated or found now. You have any doubt in this problem? Any step? You can ask me. If you do not have any doubt, I'll move on to next problem. Okay, I'll take the next problem. Design a stanchion 3.5 meter long in a building subjected to a factored load of is given factored load of 550 kilonewton. Both the ends of this stanchion are effectively restrained. So end condition is given and ultimate load or factored load is given. Height of the column is given. Both the ends of the stanchion are effectively restrained in direction and position. So it can be considered as fixed condition. And grade of the steel is given as 410. So what is the steps we need to follow? Initially, we need to choose a trial buckling class, that is trial section, or class in which case is XZ plane or YY plane, in which buckling class we should select, and based on that we should select a section. For that section we should note down properties of the section, and then we should calculate effective area, and based on the effective area next determine the actual buckling class, and then determine the compressive strength FCD based on the buckling class, and then design load PD. So this is the steps we need to follow. In the previous problem also we followed the same step. Okay. So initially what we need to do, what is the load given? Factored load 550 kilonewton. Okay, somebody is telling me so a bit slow. Okay, so for the first step we should consider what is the data provided, that is factored load PU is 550 kilonewton and length of the column is 3.5 meter. This is not effective length, this is the actual length, and end condition is provided, that is both ends are fixed. So effective length will become KL, that is 0.65 for both ends fixed, which is available in table 11 page 45 of IS 800. So 0.65 multiplied by 3.5 will give us 2.275 meter. And then we need to choose a trial buckling class because we are not knowing the section yet. So let us assume h by bf is greater than 1.2 and thickness of flange is less than 40 millimeter, which is available in table 10 of page 44 IS 800. So in this, based on this condition, buckling class about ZZ axis is A and buckling about YY axis is buckling class B. So once we got these class, next move on to selection of section. For I section, IYY is less than IZZ. Same way, radius of gyration YY is less than ZZ. So let us consider buckling about YY axis. About YY axis means the buckling class will be B. Buckling class will be B. Now open steel table, IS 800 from table 9C, page number 41, by assuming lambda value, that is KL by R value 100. This 100 value we are assuming. Okay, initially we are assuming this value. For this 100 value from page 41, FCD value corresponding to yield strength of 250, we are going to get 118 Newton per mm square. So with the help of FCD value and the load provided, we can calculate the area. Approximate area of the section required is load divided by FCD. So if we did, area is equal to 4661 mm square. We got, for this corresponding area, we need to select a section from the steel table. All of you open steel table and find this area. It should be ISMB or ISHB section. Okay, so open. Now for us, for the 4661 mm square area, we found ISMB 250 at 365.9 Newton per meter with area of 4755 mm square. This area is just greater than this value, right? So in such a way that you should select a section. This area should not be too much variation from this value, and this should not be less than this value. That is what you have area calculated. Less than that area having section you should not consider. So once we decided the section, that is ISMB 250, let us write down the sectional properties. Usually what we need to do: depth or edge, breadth of the flange, thickness of the flange, thickness of the web, area and root thickness, and IZZ, IYY, that is radius of gyration in terms of ZZ plane and YY plane. And once we note down this, we need to check what is the effective length for the web. That is D is equal to total depth minus 2 times thickness of flange 12.5 plus root radius 13. So we got 199 millimeter. So what is the next step? Calculation of effective area from table 2, page 18, IS 800. Epsilon will become 1 because yield strength is 250. So 250 divided by 250 will give us 1. So breadth to thickness ratio is 5, which is less than 9.4 epsilon. The flange is plastic because it is coming under 9.4. Hello, mute Madi. ಸರ್ ನೋಡಿ ಯಾರು ಮ್ಯೂಟ್ ಮಾಡಿಲ್ಲ.
Darshan. 18 series 020 Darshan.
So once the identified section or flange is plastic, move on to the web portion. It is depth of the web to the thickness of the web will give us 28.84, which is less than 42, and that will come under semi-compact section. The entire area is effective. In that, what is the area we got? 4755 mm square. So once we received area, what is the next step? Determination of actual buckling class. To find out actual buckling class, we should be knowing what is the buckling class, right? So h2 breadth of the flange. H is nothing but height. 250 divided by 125 will give us 2, which is greater than 1.2, and thickness of the flange is 12.5 millimeter, which is less than 40 millimeter. So based on these two values, we can choose or move further in the same line. We'll identify buckling about ZZ axis. That will give us buckling class A, and buckling about YY axis will give us buckling class B. See, these lines, if you want to understand, you should be having a open page of 44 from IS 800, or else you will definitely not understand. And once you receive the buckling class, next move on to determining the compressive strength FCD and design load PD. For an I section, IYY is less than IZZ. In these terms we have noted earlier also. It is enough to find out FCD value for KL by R YY, because from the past experience you might have noted by this time, in the YY axis you are getting lesser value. For buckling class B, as it gives lesser value of FCD, what is that? KL by R. Length is 2.275 meter. In terms of millimeter means multiplied by 1000 divided by RYY is 26.5, will give us 85.85. So corresponding to this 85.85, you should take FCD value from the table, that is page 41, table 9B, corresponding to the buckling class what we have selected. So if we do interpolation between 80 and 90, we'll get FCD value as 140.64 Newton per mm square. So once we got FCD, what is the next step? Design load. Design load PD is equal to area into FCD. Area, we have what FCD value we just got. If you multiply, you get 668.74 kilonewton. In the question, it is given 550 kilonewton. The section what we have chosen will carry 668 kilonewton, that is greater than 550. So the section is adequate but uneconomical. That means to say it is, say, almost 100 kilonewton it is carrying more, right? So we shall provide ISMB 250 at 365.9 millimeter. So this is the end of the problem. If you have any doubt, you can ask me. Hello? If not, sir, shall we wind up?
Sir, will wind up.
Okay. ಸರ್ ಮೀಟಿಂಗ್ ರೆಕಾರ್ಡ್ ಆಗ್ತಿರೋದು ನಿಮ್ದ್ರಲ್ಲಿ ಯಾವ್ದ್ರಲ್ಲಾದ್ರೂ ಆಗ್ತಿದ್ರೆ ಆಫ್ ಮಾಡಿ, ಅಂದ್ರೆ ಸ್ಟಾಪ್ ಆಪ್ಷನ್ ಬರ್ತಾ ಇಲ್ಲ.